So as Paul mentioned, today is going to be a little bit of compressed, a lot of information. You'll see a bunch of formulas, but if you sort of kind of don't understand it, or it doesn't make sense, or you don't want to understand it, don't take it too hard on you. That's all fine. The main reason today is just to get the intuition. You had your taste of first StarAi experience last time with Paul exercise. We actually will gonna step back a little bit and look at what the intuition is behind, why it's done the way it's done, and yeah, how we can use it going further. So we will be talking about Markov decision process today, and quick overview. So we'll start baby steps from Markov process to Markov reward process, and then to Markov decision process. We'll look at the couple of equations, and then we'll go into the implementation techniques and exercises, actually, how we implement the Bellman equation, how we solve the MDPs. Okay, so why do we actually look at the MDPs? MDP is, well, it describes your environment fully, right? So it gives you then the full picture of what is happening, why. And we think it is really important to understand these bits before you go any further into the parts where environment is not fully observable. All right, Markov process. So what is a Markov process? Markov process is a random process and a memoryless process. We also call it a Markov chain because it's a sequence of states with a Markov property. So let's look at this a little bit in more details. So why is a random process? Well, we can describe Markov process with this tuple, which means it's a sequence of states and sequence of probabilities. And this is a probability because you transition from state to state, or your agent transition from state to state, and each transition has its own probability, right? So say if I'm in current state, I'm an agent, right? I'm here. That's my current state. What is the probability that the next state I'm ending up on the moon? Like, probably 0. But I can walk there, for instance. That's going to be my next state, for example. That's a very high chance to happen, right? So, so why it is random? Because we don't control these probabilities. We don't control what is going to be the next state. That is provided to us by the environment. Yeah, we just basically being blown away. So if, for example, if I'm traveling on a hot air balloon, for instance, right? Okay, I'm getting up into the sky, but then whenever wind blows, I'm going, right? I have no control over the winds. And yeah, so I kind of can't really choose my destination much in a simple way. So next is Markov property, right? So what is a Markov property? Markov property says effectively that the future is independent from the past, given the present. It means that your current state describes everything that happened to you before. It contains all the information about all the previous states and all your experience. For instance, again, if I come back to myself and as an example, I'm a representation of what has happened throughout my life from my birth till today, right? I don't need to keep a copy of myself like 5 seconds old or like a year old, something like that. So that's exactly what the Markov property states. And that would help us because we don't need to keep all the memory of all the previous states. We don't need to keep the history. We just can have the current state and it has all the information we need. There is this first formula. That's a simple notation, and that's effectively what it says. That is a probability from transitioning from state t to state t plus 1 equals the probabilities of transitioning to state t plus 1 given all the probabilities from transition from state 1 to 2, 2 to 3, and so on. Again, if that doesn't make sense, ignore it. Okay, let's look at an example of Markov chain. State 1, state 2, state 3. So these are all states, and every state keeps all the information from what has happened before. So this state keeps the information about this and everything else. This state keeps information about that. So we don't need to keep all of them at the same time. We just can keep one of, like, whenever we reach at this point in time. Yeah. All right, and again, state transition probability is just a probability of ending up in this next state, being in the current state. So in a simple example, like in the previous one, right, I just have 3 states lined up together. So effectively, the transition probability between 1 and 2 is 1. There is no other states, at least here on this picture, right? But in real life, it can be like millions of states around me. Even if I take myself again as an example, I can end up there, I can end up there, whatever, right? So, but each state has its probability, and whatever most probable is probably likely to happen, but you never know what exactly is going to happen and how. Again, that's just a mathematical representation of what I've just said, right? So the transition probability, this one, from state S to state S prime, is effectively expected probability of state S prime given the current state is S. All right, Markov reward process. Everything before makes sense? Cool. So Markov reward process is effectively it's a Markov chain, but with some rewards. So now, if we transition from state 1 to state 2, we will receive something. We can just describe it using this tuple, and that's our Markov chain, right? States and probability. Now we have a reward as well for each state. We have a the discount factor, just ignore it for now. We're going to come back to it a little bit later. So, but yeah, the main thing is the rewards. So now, anywhere you go, you receive something, almost something. Again, right? So rewards are different. Rewards can be positive and can be negative, right? So positive reward is always good. We try usually within our agents, within our, like when we try to solve the problem, we try to maximize our reward somehow. So if you say you try to build an agent that trades the stocks on the market, you want your maximum outcome from it, right? Your maximum profit. Rewards can be negative as well, and because, for instance, if you battle against the time and you want to solve something as quick as possible, your time, like every single step, you lose the time, meaning the reward's going to be negative, as an example. So it happens. And 0 is also a reward, just rewarded nothing. For example, if we have an airport and the staff or whoever schedules the airplanes for takeoff right on the runway, so effectively the airport needs to make money. So how they make money, one of those is for each basically plane taking off from their runway, they're going to receive some sum. And if you want to build an agent that sort of solves this problem and handles the runway, schedule priorities, whatever, you know, and so on, you probably would want to maximize this outcome within the given circumstances. Okay. Reward function. So what its role is, it just tells you what reward you will receive transitioning from state 1 to state 2. It depends on your environment. Yeah, so basically that's pretty much it, right? It's just a mathematical thing that what it says effectively is that expected reward given current state is S would be this, right? And that's it. In many cases, we have like the same rewards between transitioning from state 1 to state 2, but not always the case. All right, so if we take all the rewards between, like, say, if I'm in this state, and for instance, if I want to build a robot that would walk from this point to the wall, right? So it will have multiple states. So if I take current state and sum up all the rewards that I'm going to receive transitioning from all those states, it will give me my total return. Basically, this is the formula again. It just says sum everything up from state t to the end. So here we go. This is our discount factor, right? We might consider discounting future rewards. It depends on our strategy, depends on how we approach the problem. So we might say that I don't care about future rewards. I only care about my next step and how much I will receive for this step, and base my training on that. Or I might say, no, I really care of the total return, right? So if your discount factor in this case is 0, basically you're saying that I don't care about the future rewards. Right? I'm just gonna take the next one and that's it. If it's 1, you'll receive everything. Now, if you look back at our nice example, so if you discounted, if you dropped out all the future rewards, being in this state is very nice. Your next reward is awesome. Moving forward, not so much. So again, it's your strategy, your approach, how you're going to solve this. Plus, it's mathematically convenient because sometimes your states can lead you to a loop. And if you say have a task to maximize your reward, if you get into this loop, it will spin there forever because the reward is going to be always maximized if you don't discount. If you discount, at some point of time, this loop will just kill the reward and it will stop because it's going to be basically 0. Okay, so again, we can sort of aim for the biggest reward we could possibly achieve. That's great, that's awesome. But sometimes we also just can aim for 0 as our maximum because we're beating against the time and we want to solve the problem as quick as possible, and that's it, right? So our maximum possible total return would be 0 in case of all our rewards are negatives. Okay. Is it clear? Make sense? Doesn't make sense? Oh.
Reward. So you said the reward equals to some function with respect to S.
Yes.
But you said it depends on the transition. So it depends on the state and the next state. So is it this state?
Yeah. Okay. So I'll answer. So the question is, reward function depends on one state or both states. Usually it's only one state, and it's either transitioning from this state somewhere, because most of the time, as soon as you transition from this state, you receive the reward, no matter where you end up in. Or it is reaching the state, right? We will be looking at the perspective of for the reward transitioning from the state. That's why it depends on S. But yeah, it's always only one state because the other one doesn't play in this. It's either the first one or the next one that's going to give you a reward. Usually it's for transitioning from the state. I mean, you can go either way, but yeah. Usually that's what you see, at least in gym environments and stuff like that. You'll receive for the transition from the state. Okay, so we have now we have our rewards and everything. We want to actually calculate the value of my current state to know like how good is this state, because if I next time I'll end up in this state, I kind of will be able to understand if I'm in a good position or a bad position, right? And for this we use the state value function. Later on we actually will be implementing the algorithm how to calculate the state value function. In our case that would be a simple table, basically this state. Anyway, we'll get back to it soon. But yeah, this is the mathematical representation. Again, our state value is just an expected total return being in the current state. Right, to actually being able to solve it and implement it, we use Bellman equations. And they all derive from this, but what we can do with the current, like with the total return, we can split it up into the immediate reward, because once you transition, you will receive it anyways, and to the next state value, right? Anyone, why is it so good or so bad? Why do we do this? Any idea? Because we had this, and we basically split it into immediate return, immediate reward, and the next step value. Yeah, that's recursive, exactly. So that will actually help us to solve it, and that's actually what we did last time solving the multi-term bundle. That's just from this expectation we actually end up here. So what it says is that our value, state value, is our immediate reward plus all the future state values which we can possibly end up in, multiplied by their probabilities. As I said, it's not always you end up in one single state. You can end up in state 1, in state 2, in state 3, being in the current state with a different probabilities. So to fully estimate my state value, I need to take all of those states, next states values, sum them up, but then I will multiply them by the probability to end up there. And if I want, I will discount as well. Make sense? Okay, an example, a simple example, Markov chain, 5 states, go in one direction, basically probability of each next state is 1. Reward for transitioning is 1 as well. And what we want is to maximize our, well, what we want at the end to calculate the state value of each of these states. So how we will approach that is basically we're going to start from, so this is our terminal state, right? Which means once we've reached it, episode is over. So game is over. That's it. We're done. We finished. Right? So for each transition, we receive 1 reward. So if we basically start in this state, we can't go anywhere. There is no way to go. It's finished. So this state value is 0. Nothing. If we look at this state, we only have 1 transition possible. So this state value is going to be 1. And so on. In case we want to maximize our return, well, in this case, our reward is positive, so I guess, well, in general, we always try to maximize our return, one way or the other. Make sense? Cool. So this was without the discounting, right? So we take each reward and just sum it up. And that's basically like the difference in value of the states is, well, big, right? If we apply the discount factor of just 0.5 on all the states, that's actually what the state values will be. So if you see, they kind of the curve is smoother, right? It's not just a straight line now anymore. So it may be handy at some point in time.
Is the value of the last state 5 equal 1 because you get to LDP reward?
Now, well, this value is 0 because we take the reward for transitioning from state to state. In this case, we don't have anywhere to transition. It's terminal. So if we end up at the end, we don't go anywhere, so we don't gain anything.
On that equation, I don't think the slide does anything with the reward. Sorry.
So in this case, there will be no immediate reward because we don't do any transitions. Basically, if you end up in terminal state, that's it. You don't do anything. So if you ended up there, like if you step in this terminal state somehow, you will receive the reward for the transition. But now in this case, you're already there. You just started there. So there's no way to go, nothing to receive. Yes?
Just to that order performance, so obviously you can't transition from one state to the next, which is the same state. You can't go.
You can have loops. Yes, you can.
So that one, so it doesn't say where S is not equal to S1. It doesn't say that.
Well, I mean, it depends on the environment you're trying to solve. We'll look into, like in future, what happens if you end up in the same state. The transition from state to the same state can give you the same reward. You just don't move anywhere, so you end up in the same state. So it can be loop. You still can have the reward for it, any reward, and it will work perfectly fine. And that's actually why we probably want this, but then it's still not going to help us much anyways. But yeah. Some cases, well, if you end up in the same state, you probably receive nothing. I mean, it depends, right? If you did nothing to end up in the same state, we'll look into the actions next. But effectively, if you did nothing to end up in the same state, you basically just stayed there, well, probably your reward's going to be 0. But if you say, if I made a step and the wind just blew me back to the same state, I still made a step, I still received my reward, but I ended up in the same state. Good? Yeah? So, yeah, but we're going from back. Right, so we sum them up, and basically 0.5 in power of 3. So if we go from back, discount factor is going to be 0. I mean 1 in this case. 0.5. No, it's 0.5 in power 1. 0. Oh, yeah, sorry. Yes, yeah. The question was I forgot it. I have the mic. The question was why actually it's 0.75 not 0.5, 175 not 125. Okay, we reached the last section, the whole Markov decision process. Again, Markov decision process is effectively Markov reward process, but now we have some sort of control. We don't have full control ever, because the environment can do whatever it wants with you. But we can now make a decision which state, like where we want to go. Again, just quick notation. So without this, it's an MRP. And plus we have an action. But once we have an action, all our transition probabilities and all our rewards, they base off the current action. Because if I'm in current state and I can go left or right, if I go left or if I go right, the probabilities of, like, say, if I go left and then the environment can blow me to some other states, or if I go right, it will blow me to other states. So all those transition probabilities will now depend if I go left or if I go right. And the reward will also depend if I go left or if I go right. It can be different. So how do we make a decision? That's basically what we try to solve and try to achieve. Let's have a look at the example, right? So this is our agent, sits there, you know, and we have, let's say we have just two actions here. We can walk away and receive 0 reward, or we can take a cheese and probably die. Again, the cheese, like the action to take a cheese or walk away is ours. Then if the agent takes a cheese, if it dies or not depends on the environment, because sometimes the traps just can't not go off or just be faulty or something. Or if it probably will go away and there's a cat there and it's just gonna die anyways, but not cheese. So you don't have a control of that, but you can decide what you want to do. So how do we decide? You already seen this. That's a policy, right? That's our strategy. What it gives us, basically, is if I'm in the current state, it tells me what action I should choose. The formula basically says that given the current state, the policy, which we call pi usually, will give me the probability of each actions I can take. Policy, well, we try to get the best policy when we train the agent. And because once we have the policy, we're good. Once we have the optimal policy, we're good to go. At the beginning, your policy can be bad. That's what you will try to improve going forward. Yep, again, just fully defines the agent, and it only depends on the current state. Yes?
Just a question, why is the discount rate is a part of the environment?
No, discount rate is a part of your strategy, how you...
But in the previous formula topic, describing a process using the discount rate.
Yeah, but this is not a description of the environment.
Description of the action.
This is how we try to determine our state value function, right? So the collection of our state values is effectively going to be our state value function, because as soon as I give it my state, it should give me back how good or bad my state is, right? So this is how we approach to solve it. So it's not an environment. Actually, discount factor is our actual policy, our tactic, how we're going to approach. Do we want to discount in future? Sometimes if you don't discount, it might not work. You might hit the loop and you won't find the best policy or anything. Sometimes you don't want to discount, really. It depends.
So it's not, I feel actually it could be partially dependent on the environment. Some environment will reward you on your final action, but some will reward you on incremental. So
but it's different. That is just the reward that the environment gives you, right? So it's not discount. It doesn't, like, if say you're like, if you're in this state and say for this transition you can receive only 0.1 of a reward. For this state you can receive 1, right? It doesn't matter if you're here or if you're here. For this transition you will always receive 0.1, and for that you always receive 1. That's what environment gives you. Even though your future reward can be smaller, that's how environment rewards you. That's not what we discount. But we can further discount these different values just to sort of discard like the long-term rewards, because the episode can be very long. And effectively, if we say want to maximize our output, if your episode is long enough, any policy, any action, any route can be good, because I mean you run it forever and your reward is infinite, right? So that's why we want to discount to sort of prevent these things from happening. It's just convenient mathematically.
Are you also saying there's some disconnection? Well, states and actions are two different things altogether, and action doesn't necessarily put you in a definite state.
Yeah.
Oh,
Yeah.
We're gonna talk
yeah,
about it.
yeah. I was just saying how that differs from what we were just talking about.
Yes, yes. So your action is something you can do, but then it doesn't guarantee you ending up in another state. Okay. All right. So again, policy doesn't depend on the history. Like, remember, our state contains all the information about our previous knowledge about like everything, right? So if I have a policy pi and I give it my state, anytime, anywhere, like even like 5 years from now, whatever, it should give me exactly the same results back. It might be a bit confusing, but for instance, if I'm running for 5 years, like training for 5 years, and come back to the same state, actually it's not the same state anymore, right? Because I have a knowledge of this 5 years of running. So in this case, policy can give me different stuff. But if I have the same state, it means I have the same knowledge, exactly the same knowledge. I'm as green as I was 5 years ago, and I ask policy what action I should take. It should spit out me the probabilities of each action I'm supposed to take or I can take. That's why it's time independent and it's history independent. Okay, so we have our value functions. We already saw the state value function for the MRP. For the MDP, it is the same. It's the same expected total return given the current state, but now following the policy pi. Because if you follow the different policy, your expected return can be different. Let's look at an example. So for instance, now we have this chain. And say for each transition we have a reward of 1, and I'm here now. So I have two actions. I can go here or I can go here, right? So if my reward is 1 for each transition, if I go up, my S1 value is going to be 1, right? Because that's the terminal states, because we don't have anything else to transition, so we end up the episodes here. So it's just going to be 1 transition, so the state value is 1. If I go down though, I have 2 transitions. So in this case, my state value actually is going to be 2. That's why now our state value functions depends on the policy we go. And the policy will tell you, should you go up or should you go down? Make sense? Okay. So now we have an actions. So we actually can estimate our actions, how good our action is, the same way as we do with the states. Looking further, it's actually more important because your action determines where you end up in, one way or the other, and that's how you can actually improve on your policy. But, so how do we estimate our action? Effectively, we just take all our total return for taking each of the actions. So if I have 2 actions here, I can for each of them calculate the value because I know, like once I take an action, I know when I end up and I know what my total return will be. So the formula, what it just says that again, that's your Q value. You'll see in the next day as well. Our action value is an estimated total return given the current state S and taking an action A. Again, same example. So in this case, this action value is 1. The down action value is 2, because if I go up, I receive 1. I go down, I receive 2. Bellman equation. Again, we saw Bellman equation for state value. That's it. Nothing new here. And we have a Bellman equation for the action value function now as well. It's exactly the same. It's just we split up this total return into immediate reward and the next state value. Right? So expected immediate reward plus next state value given the current state S, and we can discount it again if we want to. Well, sorry. Oops. Yeah, but same stuff, just different letters, Q and V. Yeah, I mean, next action value, of course, not the state value, because we're now going from action to action, and we want to calculate our action values, given we're taking the action A at the moment. Sorry, guys, confused you a little bit.
Sure. Is this? I'm confused because the left Q has 2 arguments and the right Q has 4 arguments. So
No. So Q depends on the state, and so basically, what is the value of action A given state S, right? So this basically says what is the value of action T plus 1, of all actions T plus 1, given the state T plus 1, if my current state is S, and I'm taking action A.
So there are 2 different Qs.
It's the Q of the next action. So look in here, right? So if I go here, right? So my action value here is the reward for transitioning plus the next action value, right? So I'm gonna receive the reward of 1 for this transition, and my next action value is 1. So yes, this is the next action value.
I have a question. Can we go back to the chain example? So the upper arm, the state value is 1, and lower arm state value is 2 plus 1, 3.
No. That's already calculated values. It's not a reward. It's action value. So yeah, sorry.
That number 2 is already added.
Yeah, it's an action value. It's how much this action worth. In all the cases, coming back, is we always take here the next step. That's what helps us.
So just going back to that equation, that one. So is that saying that all subsequent steps have to add up all possible actions to meet possible success of state?
Yeah. Yes, we will look into this like in 2 slides.
So by being recursive, because Q as state is already in the equation itself, and you're essentially saying in this current state, you sort of need to understand the end of the episode or it is to be able to calculate the first action.
Yeah, I mean you always have action value function and state value function always. It just can be bad. So you try to improve it with every episode you run, but yeah, you will always have your action. I mean, in the worst case scenario, your next action value is 0. That's where you start usually, right? Because you've never seen this action before. So whatever, nothing, 0. We'll have an example later on, which probably will make it.
Just quick comments. This is the state AI's S, depends on the future policy you pay on the future loans, but you are not sure what's going on in the future. So you end up with a loop like because you current state depends on the value of current state depends on the future, but in the future it depends on the future. I end up with a loop.
Yeah. So well, that is a complex example that you're gonna solve next lesson, next day, next Tuesday. Effectively, in the MDP, we know the environment. So we know where we start and where we end. we don't have uncertainty in this case. We know all the state action space in the MDP, right? So that's just basics. And yes, it's not really applicable in the real world because we don't know the environment, or even if we know, it's too complex to describe with this. But that just gives the intuition how it's been applied. There are methods that have been applied in the unknown space, yes, but it's different techniques. So if we're lucky, we'll look at this today, briefly. If we're not lucky, Tuesday, but next Tuesday, but you will be working on that in the future because that's actually where you're aiming at. That's what you ultimately try to solve. So if we just break this previous Bellman equations further, again, guys, that's just formulas incoming, right? If something doesn't really settle in, that's all fine, just ignore it. I mean, it's a lot of information here compressed into a small, quick presentation. You'll get these formulas, and we'll implement some of them today, and as a homework as well. But yeah, I mean.
Not really good at math. That little a and that funny e and that.
I'll explain. I'll explain. So basically, how we calculate if we take our Bellman equation, this one, and basically put it into like a proper formula we can actually implement, we basically sum up all possible action values, and this basically says that every action that is part of our action space, right? Because we can have different actions, but we only look at the actions that belong to our action space. So we take all of those values given state S and multiply them by the probability that gives the policy to us. And we sum them up. And that's going to be my state value at the moment. So we basically now rely for action values to calculate the state values. And the opposite. So now how we can calculate the action values. So given the state state S and taking an action A would be just a reward that we're going to receive for transitioning from this state and taking action A, plus all possible state values which we can end up in multiplied by their probabilities. And this again just says that our future state, the next state we end up in, state S prime, is part of our state space. A little bit example probably will make it easier. So if I'm in state S, the white dots are states, the black dots are actions. And that what shows what can happen actually, right, once you take an action. So if I'm in state S and I'm taking an action A, I got my reward. That's like my part is finished. Now I'm out of control. Now there is a probability to end up in either this state or this state. This probability to take an action A or the other one is defined by the policy. These probabilities defined by the environment. So we don't have any control of that. So if I say I take action A, I end up in state S prime. My state value would be the reward plus sum of my next possible states values multiplied by these probabilities. And my action value would be taking action A, and again, get a reward. Because if I'm in action, step back. In state S, I will sum up all of these values because we have a policy that determines where we go, so we have different probabilities. But we want to consider all of them to say how good my state is because it sort of determines, its value. Because I can take action. I say this action has a value of 100, this has a value of 1, but probabilities might be different. Say this might be 0.1 and this might be 0.9. So we likely end up here, but this will actually have more weight on this, on the state value. So we will sum these values up with the probabilities. And say about the action value, we will sum up all the states we end up in, multiply by the probabilities we have for them. But for the action, we always receive a reward, no matter what.
So, can an action lead you to different states? So here, A actually leads you to S dash, and then there's a point in white circle which
yes,
has
that's well. I mean, I just didn't put the letter here. It can be state prime 2, whatever. I mean, yes. So action can lead you to multiple, like a number of states with a minimum of 1 and maximum of whatever, right? So, and you never know where you end up in. You can guess, you can estimate, but there are probabilities, unless it's a simple chain where you just all the probabilities are 1. But yes, that's the thing. And then again, if you have a policy with a probability of each action, like say, you don't have a determined policy that always tell you take an action A, you can either take an action A or the other one. Depends.
So it's assuming that the state space is non-deterministic. In other words, like if I say action go up, that I'm not going to necessarily always go up. There's a probability that I might fall into and going right instead.
Well, your action to go up, that's your action. That's you control, right? So that's your policy say go up. That's what you can control, right? But then you cannot end up on only up. You can also be blown away to other direction, right? So, and that's environment. That's we can't control. Say, if I'm now traveling not on a hot air balloon, but on a boat, I'm rowing in the ocean. So I can sort of like try to direct myself somewhere going south, but then there are tides and something else and waves and storms and something, so it can blow me away like completely into a different place, right? But at least I tried to go there.
So if I understand, it's like, for example, I'm playing chess and I do a move, so that's my action, and the S prime is what the other one is going to do, so maybe I'm going to end up in checkmate or something?
Now, in chess, I guess it's more certain, because in chess you take an action and you actually go there. That's going to be your state. I guess the counteraction can. Well, yeah, you're right. That's a good question.
Sorry.
It's alright. It's interesting.
Because I don't know what the other one is going to do. It's almost
Yeah,
state is going to be different because of the environment I come from.
Yes, effectively yes, because the action of the opponent is controlled by the environment, or by another agent, anything. So you don't have control over it. So yes, effectively, whatever happens to you after you move there, but you transition to a state. But yes, if you say been beaten or not in this same state, makes the state different, and the state value is different as well. Boom. So what we try to achieve at the end of the day is to find our optimal functions. Because once we found an optimal function gives you it tells you exactly how good this state is, how good is this action compared to everyone else you have, how good is your policy, right? So that's what we try to achieve. Once we got our optimal functions, we solved the problem. We're done. We're good. Because and we have of course we have equations for it. Ignore this, right? So if you want, you can look at this, you can take it, but if you don't want, too many letters, whatever, just this is good enough. So basically what it says, and we mark with a star our optimal functions. And effectively what it says is that our optimal state value function is being like the maximum of all our action values available to us being in the current state. And same about the action value function. It's again, but we will receive the reward in any case, so we always sum it up, because once you take an action, you receive a reward. And then again, effectively, this is this. Right, so if you ignore this and put just V star of S here, that's what we end up in. But in like a difference for the action value function, again, we will sum up all our possible states we end up in, because again, we don't have a control, and there is always will be some probability of ending up in one state or the other.
The optimal policy is not guaranteed to give us the maximum reward. Right?
It does. So optimal policy always has an optimal value function, always action value function. Always gives us that.
What about the probability of the policy will give me action?
Yep.
We said the action doesn't guarantee the next state.
Yeah, but we take into account all of them, including the probability here. Right? So if we kind of take only the best one and okay, there's a probability ended up there or there, but we took the best action we could. That's basically, we can't do better. We only can take the best action we can, and we need to determine the best action. And we determine the best action based on actually the possible state values we will end up in, right? So possible best, the possible states.
Here is the English rule, because it says it's maximum expected probability. You can fetch because it's
Well, yes. I mean, the probability is not always like set in stone. I guess it will depend, and in the more complex environments, it will also depend on what you have done before and stuff like this. But in a simple example, it's like whatever it is, right?
Could you explain what's when you do the max? What's the argument or variable you max over?
Thank you. So, you mean it's maximum Q value of like maximum maximum Q value or optimal Q value of all possible action. Like, so basically, if you have action A or action B being in the current state, and action A worth 100 and action B worth -1, and your goal is to optimize the return or get the maximum return, you ought to take action A because it's way more rewarding than action B.
Just that last question. So you're not taking the same action at every step, are you? It's got the same A values.
If it's optimal, we assume that, well, I mean, it can be many optimal actions because they give you the same result. But yeah, you only take those that give you the best result. So if it's multiple actions that lead you to the same result and give you the same reward, yes. If it's only one, you take only one.
Is that saying you take the best action at each stage?
Yes.
Okay. So I just don't see how do you get that from the notation? Or just in there somewhere.
Which notation?
Like in the bottom line, like it's probability of S transition to S prime, given A. And I'm just saying, with that A there, that little A there, is that
Yeah, but once you took this action,
okay?
you don't know in which state you end up, right? You can end up in one state or the other. Based on this state, we then need to take again the best action. So that's what it says, right? But then we will sum up all those states and take in the best action from there and multiply it just by the probability, because again, if my reward is very high but the probability to achieve it very low, it should be reflected in the total action value.
Because that's not A prime, is it? The A,
Where?
the bottom one.
Yeah. It's not A prime, it's A.
No, but
Because you took an action A, 2 more slides. Or 3 more slides. Yes. Right. So what we want to actually get by using those optimal action values and optimal state values functions is to get our optimal policy, as I said before. And yeah, once you get, because you can, like now, once you know the best actions that can be taken from the state, you can actually update the policy, even if it says like take any action or take the other action, because the previous policy was thinking that it was the best action. Now you know that, okay, the other action is actually better. So you can update your policy and say that, well, I should be taking the other action. So once you have your optimal functions, you can update your policy and achieve and iterate again, achieve your finally optimal policy at some time, iterating over and over and over. We'll look into that as an example. So let's look at the ways how we can actually solve this and implement these like simple agents to solve simple problems that utilize MDP. And as you noticed already, it has a recursion in it, so we can apply the dynamic programming. And it's just a reminder, so I'll skip it. Dynamic programming approach is fairly simple. I'm pretty sure we have a smart audience here, so I bet most of you have used that, and if not, even that's like you probably actually have, but you just don't know about it. So how we approach it, we just take a complex and big problem and we split it into small subproblems and solve them separately, and then combine the results. Yeah, we need like a couple of requirements to satisfy, which is like it has an optimal substructure and like the problems should be overlapping really. Otherwise, you can't really mix them up. But that's pretty much it. MDP satisfies both, so we are good here. So what we will be doing today is solving the prediction problem, or we'll try to actually generate our state value function following the policy. So that would be our prediction problem. And for homework, you will actually go further and try to get your optimal policy from your state value function whilst you get the optimal state value function for the given policy. So you will basically iteratively applying both like things, first analyzing your policy, evaluating your policy, and then updating your policy, and then evaluating again until you get the best optimal policy. And for those who are really interested in, there is another step further where you can solve it much faster, doing just one step ahead, one step look ahead, sorry. Just basically evaluating one next possible step and updating your policy straight away. So that's for those who really want to sort of go to the end. And whoever posts the solution to the both homeworks will get a cookie from me next time on the forum. First person. Okay, so let's look at the example before we actually jump into the code. And is it readable with this? Okay, so let's assume so that's actually StarCraft, and let's say you want to move this unit to a corner. Simple thing. So I mean, StarCraft is a complex thing actually, but we'll simplify it to a grid problem, right? So say that's again for a reminder, but let's assume that this is just a grid of all possible states, and once we reach any of the corners, we're done. We're good. We solved the episode. We finished the episode, right? So let's be in here. Let's figure out what actually our each state value is, and for that we're gonna and like we have only 4 actions. We can go up, down, left, or right. Transition into the next state, and yeah, we just want to like get our optimal state value function for the given policy. And the given policy will be just pretty dumb. It will say take any action with the same probabilities. So go in any direction is going to be 0.25. But a part of the policy for now, how we will actually, using this, and we forget about policy now, but how we will solve it. So let's try to do it together before we actually jump into the code. So this is our beginning, and again, it's very, very simplified thing. It just has 16 states, right, from 0 to 15. These two states are terminal, which means we want to reach them as quickly as possible, right? And we begin with this. This is our initial state value function, which just says that every state is worth 0. We haven't run it yet. We don't know what's happening. So that's what it is. So let's try and evaluate this whole thing and calculate our real state values. So for each transition from state to state, you will receive a reward of -1. Why? Because we want to achieve the terminal state as fast as possible. That's why we use a negative reward. If you're in a border state, you can go up, for instance, here, or left here. You will receive a reward of -1, but you will end up in the same state. So basically, you take an action, you can take an action, you will receive a reward, but you're not going to transition anywhere, right? So let's try and calculate, let's say, this state value, right? So how do we reach this state as quick as possible, keeping in mind that we can go up, down, left, or right? What is our next step? Up, left? Which one?
Either.
Pick one. Up. Okay. So we're going up, right? So our initial state value is 0, so we're trying to calculate this state, right? So we're going up and receive the reward is -1. Anyone has an idea what is the value of this state will be? -1, -2, -4, -3. Any reason why? Yeah.
Any discount factor?
No, we don't discount. We take everything into account, and the probability of transitioning to this we have only one state, right? So you can't go up and end up here. So you always, if you go up, you always end up here or here. I mean, it's always probability of the transitional probability is 1. So it's always the same state if you go the same direction. Okay, so once we if we evaluate all the steps, so we do it at the same time for each state. This is going to be our state values. Why? Because we're here, and our state value, if you by chance recall, is immediate reward plus next state value. So if I'm here, I move up, my immediate reward is -1. My next state value is 0. So it's -1 plus 0 -1. And that's for all the states except the terminal states, because here we don't receive anything, we don't go anywhere. We just reach them, that's it, finish. Make sense? Yes?
What about all the other possibilities that you have?
So we don't have any transitional probabilities here. It's always 1. It's always whenever you go, you end up there. So if you go left, you end up here. It can't be that you go here and end up here.
And how do you choose?
Well, it's just this example.
Okay.
This is the environment that always sort of sort of environment, right? So like chess, you make a move, you end up somewhere. Well, sorry, chess is way more complex. But anyway, yeah, it's like you make a move and you end up where you actually were going. So, yeah. Yeah. So we just did. We evaluated every single state now. At the same time, that's why we always look at current. This is our that was our current state value function at the beginning, right? And then initial state zeros. This is our new state value function once we calculate it all. We calculate it for every step, so we don't consider into account newly calculated values.
Sorry, how about different actions? Because for every state there are 4 actions.
So again, we just for this particular example, we simplify. We decide which action we choose. That's why I asked you which way you want to go, right? So here, in fact, whenever you go at this state, it's always -1 because then just one transition, reward -1, next state value is 0. So this iteration is always -1 probably. But for this example, we decide where to go. So say we humans, we already solved this problem, right, in our heads, easy enough. So we say we know optimal policy now. So we say evaluating our optimal policy. Now let's just calculate the state values for that. So we're always gonna pick which direction we go when we calculate, and that direction is correct, unless you pick the wrong one, which probably you don't want to. Okay, so, and we apply all of these things recursively, right? So first sweep gave us this state value function. Now this is our source of truth. We apply the next sweep. What would be the value of this state? -2. Agree?
Yeah.
-3 because you end up in -1. -1 transitioning, but then you add the -1. It's a -3.
So where is the third -1 appeared from?
Sorry, I thought that you
Sorry, to make it clear. When you start new evaluation, you don't take into account your current state value. You calculate in your current state value, right? So assume it's, well, 0, whatever, right? But so you don't take this into consideration, right? So -2, agreed?
Yeah.
What about this one?
Doesn't change. -1.
If you go to left, -1.
You always go to the left because you know that it's wrong.
I'm going left.
Yeah, -1.
-1.
Yeah, stays the same.
Agree? Correct. So as we see, our state value function actually now starts giving us the hints which way we should be going. A part of some blocks. Say if I'm here already, looking at my state value function, I actually already know that, okay, I should be going either left or up. I shouldn't be going right, because this value is worse than this. And we try to maximize our return. Right? And so on, applying exactly the same logic, we do another sweep. And this is our now source of truth. This is our state value function, right? That's what we receive. Does it make sense where we take the 3 from? And so effectively, this has converged, right? I mean, we have optimal state value function. Looking at that, I know exactly which way I should be going. In any state I'm ending up in, so starting from, I know exactly how I can achieve the maximum return just looking at my state value function. So that was picking the policy. I mean, picking the action ourselves. So we already solved the problem before we actually looked at it, right? So we know the best policy, best actions to take in this case. What if we apply the policy? And remember our dumb policy that says pick any action I don't care? So again, we start with the zeros, beginning. this is our first sweep. I don't want you to pull out the calculators and try to start multiplying probabilities on this, but effectively -1 is here in the first state, because it's whenever you go, you receive -1 reward plus the next state, which is 0, and then you multiply it by the probability, which is 0.25, but we have 4 actions. So it's 0.25, 0.25, 0.25, 0.25, 1. First sweep. Second sweep is more interesting now, because of these values. Does it make sense where it's coming from?
Because it's stupid policy, it goes to the wrong direction as well.
Yeah, so effectively when it goes here, it receives 0 and -1, but then it's multiplied by the probability, which is 0.25. And then this, for everything else, is going to be -2, so 0.5. So 3 times 0.5 plus 0.25 minus 175. And the next sweep will take you, we'll need to calculate to calculate. It's actually 2,475. Just 1 feet.
So each step is an equal probability moving up, down,
Yes.
or right.
Yes. So our policy says that pick any action with equal probability.
Yeah, and given that it's equally probable when you sum over it,
Yep.
that you're taking the average.
Yep.
Because it is.
Yep.
That's why I get
Yep. Okay. So again, we see it's already converged, right? So we basically got the best value. Actually, if you run it further with multiple loops, it will converge to the point that the difference between previous state value function and the current state value function would be like 10 to -5 or something. And it will converge around when the diagonal values is around -20. You will actually see this in the implementation. We will implement the algorithms for this today.
So, I think we might extend. I'm kind of confused. What's the difference between this slide and the previous slide?
In the previous one, we were picking the value, the action, which one to take. So we were pointing which one is the best action. So we didn't take into account the probability of actions when we were calculating the state value, right? Because we nominate this action, this probability of 1. So that's why the numbers are so beautiful, right? Just round big numbers. In this case, we actually take into account the probability of each action. That's why it starts losing the values here and going further here as well. Because now each value for each action we take is multiplied by its probability, which is 0.25. That's what our policy says. Because policy says every action is equal, each action is equal, right? So it's 4 actions, total probability is 1. So 1 divided by 4 is 0.25. So probability of each action is 0.25.
Can I say these two slides are basically the state value function under different policy?
No, it's exactly, I mean, yes. Because here we were using like optimal policy, effectively, because we were picking up the correct actions always. In this case, we don't know the actions. We have all of them. So we need to take into account all of them. Even like stupid actions like going up here, for instance, which makes no sense, or going, like, I don't know, down here. Right.
Are you looking forward multiple steps?
Yes.
Yeah.
I mean, no, in this case, it's step by step.
Okay.
So it's 3 steps. But yeah, so you run it in loops until you're satisfied with your state value function. And usually how we satisfy, well, we sort of measure the difference between this and that, like the previous one and the current one, the newly calculated. And if this difference is very small, means that your function almost doesn't change, means it's all good already.
So
yes.
Just to practice, so the previous slide was just an ideal setting.
Yes.
This one is
Yes.
the real thing.
Yeah.
And would you treat that like as a matrix of like this problem, or is it gonna be like that, like when you actually calculate the function, like the value?
If you take exactly this problem with exactly this policy and run it, you'll receive exactly these numbers. You'll actually see it in 10 minutes. But yeah, it's a real solution of this very cool and real problem. Good? So yeah, as usual, collabs, I will post the link now on the forum. And it goes to the same place, which is DeepRL course. So feel free to grab the link, make a copy to your drive. And once you're ready, we can kick off. So in this example, we will actually be implementing this policy evaluation thing that we just looked at. And so as last time, you need to, you open it only in the read mode, so you need to go to File and save a copy in Drive. So the screen, I guess, is not readable whatsoever. You guys good? Does still anyone have any problems opening it, copying it? Or can we roll? Okay, I take silence for all good. All right. So you can either follow in your notebook or you can just look at what I'm doing. But okay, so again, we will just implement the policy evaluation problem here. We'll have exactly the same what we just saw in the slides before, a dump policy with the equal probabilities for any action, and the same size of a Gridworld. If you wish in the future, you can change the size of the environment and play with it further, but I mean, effectively it's the same output all the time. It's just the bigger the action, the state action space, like the state space in this case, like the longer it takes to converge. But that's pretty much it. So what we'll need to install, because Gym, unfortunately, doesn't give you the Gridworld environment, probably too simple for them, I don't know. So we'll actually have to use some implementation that I shamelessly stolen from the web. And if someone has a problem executing the first cell, because Colab was actually playing with me and was either do this or either do that, so we need to either uncomment one thing and comment out the other one, or the other way around. I don't know, it feels like it depends on the weather, where it's going to fail or install. So I'm good through the installation, and the import state, we're just going to import everything, so we're going to use NumPy. Often we use it. pprint is just a simple utility that's going to format our metrics in like more human format than NumPy gives us, and we import the environment, the simple Gridworld environment. So a few steps about the environment, a few words about the environment. First of all, the environment gives you the transition probabilities, and it's accessed by env.p. So effectively, if you call env.p with the state as a key and action further, you will receive a transition tuples. And why transition tuples? Because theoretically, we can end up in different states, remember? In this example, it's always going to be one state, so it's always, it returns you a list of those transitions, but it will be a list of one. About the symbols we use, effectively, these state space is from 0 to 15. The action space is from 0 to 3, just for convenience, but yeah, it can be anything. So yeah, these probability matrix is the most important thing we need. We also have the total number of states, and we have the total number of actions. Here also the states are not in the form of matrix, it's actually just an array of 16 numbers, 16 values. And that's what's gonna our actually function, state value function will look like. Okay, so that's actually the formula that we're gonna implement. So remember, that's why it was so useful. Just a reminder for you for the future, but okay, so let's do step by step. Really, you can solve it within like 10 lines of code if you want to. I split it in bigger chunks so it's easy to show. But of course, it's a bit of an overhead here. So first, let's implement how we calculate the single state value, right? So, well, here's the code, if you like to look at the code. But exactly what we do, we start with we pass to the function our policy. And our policy is SA matrix, which is basically, you give it a state, which is a number from 0 to 15, and it gives you back a probability of an action. Right? Again, here, it's just going to be one single probability because it's for every action is 0.25. But theoretically, it can be different. Well, in real life, it's actually going to be different. But anyway. We also pass it just a single state, which is just a number. We pass it the environment, just so we can access the state transition probability matrix, and with all those transitional tuples. V is our current state value function. That's basically given it's a state, we will receive what is the state value is at the moment. And the discount factor, in case you want to discount, and if you wish, you can play with it later and see what's the difference in the results. For this example, we're just going to use 1. We're not going to discount anything. So we initialize our current state value, which we try to calculate with 0, because we don't know it, right? And then, well, what I'm using here is just to enumerate over every action and its probability, right? So our policy for the current state will give us the probability of this of each action, and what this returns, the enumerator just returns you the tuple of an action and action probability, and this tuple is going to iterate from 0 to 3. It's just for the convenience. You could also iterate over each action on top of that and use it in here, but it just basically saves you one loop. So then for each action and its probability, we will take our possible transitions. And again, our environment is just, I guess, to follow the Gym API. It returns you the list of all possible states and all its probabilities and stuff like that. In our case, it's going to be 1, but anyway, we're going to loop over all of those theoretical possible states. And we also split it straight away into the probability. So that's what actually the environment returns you in the transitional tuple, right? It will return you the probability of the current state, of the ending up in this new state. This new state, the reward you're going to receive, and the flag if it's a terminal state or not. We're not going to use it now. You might find it helpful doing the homework. Basically done indicates that we reached the final state. And then we apply our formula. Effectively, we take our reward, we take our next state value, discount it. What just happened? Okay, my Mac played with it. Sorry guys. There we go. So then we multiply it by the probability by the transitional probability, which will be 1 in our case, because we have only one state we end up with. And then we'll also multiply by action probability, which in our case is 0.25 always. And we sum this up to our initialized state value and return it. Make sense?
So V is a 1 vector or is 16 vector? What is V?
Sorry?
What is V here?
V is our current state value function.
16
So this. I mean, any of these grids, 16 values. Yeah. So it's a matter. Well, I mean, yeah. At least we give it an index, or it could be a dictionary if your state is not from 0 to 15. Yeah, and that basically gives you what is the current state values. Okay. So next would be to actually iterate over all the states and calculate each state value, right? So again, we pass to this function policy just to pass it further to the state value function calculate. And again, we give it an environment, we give it current state value function and a discount factor. So what we do here, we create a new state value function, which is basically an array of zeros. That's a numpy command that's going to return you an array of zeros of this size, right? And we also have a delta here. Why we have a delta here? We will need it to determine when we need to finish. Because at the end we will run it in an infinite loop, and so we need to some point of time we need to decide that this state value function is great. We don't need to iterate. We need to stop. We will see the next step. But in this case, we will be calculating delta here because it's easier. So we are iterating over each state. It's just a range, so it's an array of 16. For each state, we calculate its new value. And then we calculate the delta, basically taking the maximum between the newly calculated state value and the known one. And basically, once this delta is small enough to stop, we will stop. And we basically assign a new state value function. And after we finish for all the states, we return the new state value function and a delta. And here we're done with the first sweep. actually intuitive view. Okay? Make sense? Cool. Basically, now we have our main function that does nothing except initializing some values and iterating forever. So that's just a little bit of description for you for later reference in case you want to come back and read it. But so what we're going to do here is create our initial state value function, which is again zeros. That's where we start. And then we start the infinite loop. We apply our function to run a full sweep, every loop. We calculate a new state value function, and we basically replace in this line, just replace the existing state value function with a new one because we don't need it anymore. And we also get the delta. And I forgot about one thing, because for this function we also have a theta, and that's basically our indicator when to stop. As soon as your delta is smaller than this number, we break the loop, and we've got our optimal state value function for our current not so great policy. So now we can run it. So we just create a random policy here. Again, it will create an array of ones. It's a NumPy function of this size, of the size of each state on each action. So it's a matrix. And then we basically divide by the number of actions. So this is if you haven't met it before, it's a NumPy thing that where you can apply and basically transpose it across the matrix, just one calculation. So effectively it's going to be every value of every cell in the matrix is going to be 0.21. And that's our policy. Ooh. Why don't I? Because I didn't create the environment. Because I skipped this step. Sure. Okay. Again. Here we go. Then we evaluate our policy basically using our function. Simple enough. And this is V now is our optimal policy for the given optimal state value function for the given policy. And we can print. So here's our matrix. It is not symmetrical, and I just spotted it the other day. And I have a suspicion that that's the environment spitting out a little different numbers, because even in the tests for this environment, that's what they expect from this problem as a solution. So honestly, I don't know why it's that. It should be symmetrical like we saw. So something is wrong with the rewards being.
It is symmetrical.
No, this value should be 13. Sorry, yeah, my bad. I think it wasn't symmetrical actually the other day I ran it, but anyway, so it's good. Ignore me. And we have a simple test that would actually indicate that you got what we expect from it.
I have a question. Your previous slides that mentioned about dynamic programming-based approach, but this is not a dynamic programming-based approach.
Sort of, in a simple way. Because we solve it for one state and we apply this solution on top iteratively. So, sort of.
I mean, I imagine if you use dynamic programming, we don't need this iteration steps. We should be able to just solve it in one go.
Well, I mean, yeah, that's a homework number 3 for you. To solve this in one go. It is possible. It's very simple. Yeah, I mean, we just apply iteration here. We don't really kind of bother much, right? There is a way more efficient ways to solve it within basically a sweep. So, and that's homework. I guess that's it for the example. I will post the homework today, shortly, sometime at night, maybe tomorrow morning, maximum. Yeah, but again, just one second. Whoever solves first other two gets a cookie. Big one. Why? Well, because the difference, like between, like, I mean, it's like so sort of we determine that it's good, sir. No, we don't discount here. It's just because we apply the action. Like if we look here, right? So our state values, they degrade slowly because of the terminal states of the zero. Like effectively, it's just like put the math into the formula, like put the numbers into the formula, running over and over again, because you always have a zero here. So that would start decreasing these values. That would start decreasing these values slowly. So at the end, like they will still continue to grow, but the speed of growth is going to be like this, right? And that's why we have a theta. So at some point of time, we say, okay, well, it's good enough for us. I mean, if it's not good enough for us, we can decrease the theta to like 10 minutes in minus whatever, or we can even run it forever if we want to. But what's the point? So we need to determine where we stop. So these values degrade with the time. Slowly it grows, but exponentially, right? And yeah, that's why we need to cut it.
Sorry, just a quick question. If you add a decay, would the convergence rate be faster? I guess, is that reasonable?
So the question is, if we add the discount factor, would it converge faster? I don't know, but my intuition says that no, because now we know exactly, like with every sweep, we take into account every further state, and we basically know, even if we're here, we know that it's good to go there. But on the other hand, if I'm here, and I'm just taking into account this state value, but I'm not taking anything else, that might affect actually my initial state, and actually it can be worse, at least. Or in this case, actually, it might not even make a difference. I understand now.
So what's the purpose of
In
that?
other problems, especially when you, like for this you don't need it. That's why we don't really use it. But in the problem, say if you have a loop, say for instance, if you, I don't know, have an action here that would actually iterate over and over and giving you like, I don't know, like small number, you can stuck with this state forever. I mean, in this case, I don't know if you can really discount. I mean, should you? But if you have a positive reward and you try to maximize it, so if you're stuck in even in super ineffective loop forever,